Okay, so at the end of the last video, we were talking about transition elements uh, um, giving up a specific number of electrons to create ions that had a certain charge. And this table is the table that I told you I would. Now, I'm obviously on a test not going to copy the whole table. I'll just give you the charges that are going to be present for the elements that I want you to know about on the test. Okay, so because a transition metal can potentially give up a different number of valence electrons depending on the circumstances, the actual number given up in a certain situation is usually designated by a Roman numeral. Okay, and here's what that means. So if I have two different types of iron oxide, this would be iron oxide and this would be iron oxide based on the chemical symbols, but they have different numbers of ions in them, and that's because the iron has a different charge for each of these. So if I look at oxygen, oxygen normally has a -2 charge, and I've got 3 of those, so I'd have a total of -6 oxygen charges, which means I'd have to have +6 charges for the iron component, and since I only have 2 irons, that would mean each iron would have to have a +3 charge. And I'm going to show that in the name of it by saying iron 3 oxide. That's the only way I can do that. Likewise, for this form of iron oxide, the iron has a 2+ charge, and these are two different compounds. If iron has a 2+ charge, it's a different iron oxide than it is if it has a 3+ charge. Okay, so, and we'll talk more about this when we talk about naming in the next part of this. But for now, we have this basic understanding of the different possible types of ions. If I have metals or nonmetals in columns 1A through 7A, and I didn't include 8A because they don't react, right? They don't form ions. Their outer shell is already filled, and they don't have the ability to take or give up electrons. Okay, so metals and nonmetals in columns 1A, and we have that table that shows if I'm in column 1A, I give up 1. I have 1 valence electron. I give up 1 electron. If I'm in column 5A and I'm a metal, I give up 5 valence electrons, and I have a 5+ charge. Or if I'm in column 7A and I'm a nonmetal, I'll have to be a nonmetal, I take 1 electron if I'm in column 7A. So we've got those monoatomic ions, those elements. We also have transition metals, and again, that's just the element by itself, so it's a monoatomic ion. So if vanadium gave up 5 valence electrons and it would form a charge of +5, that would be an example of that. And then we have this list of polyatomic ions that are made up of nonmetal components. So the sulfate, for example, has a sulfur and 4 oxygens, but we don't talk about the sulfur and the oxygens individually. We talk about it as a unit, the SO4 unit, or the sulfate ion. Okay, so in the next page here, we're going to go to the next page of notes, and we'll see how to put these together to create the formulas for our ionic compounds. Okay, so in this section of class notes, we're going to talk about the formation of formulas for these compounds. So we say now that we know what the basic types of ions are and how they're formed or come about, we need to learn about how to put them together in chemical formulas and then how to name the chemical compounds. And the naming of the chemical compounds will occur in the next part of this discussion. So you're aware that chemical formulas describing compounds are combinations of atomic symbols of elements that make up the compound. So if I have sodium chloride, it's a combination of the sodium atomic symbol and the chlorine atomic symbol. Okay? You're aware that the formula tells us the specific number of atoms of each element in the compound. the ratio of the number of atoms of each element to the number of atoms of each of the other elements is what we're going for there, and it's a constant. So if I have an ionic compound that has 2 ions of magnesium and 1 of oxygen, MgO2 or Mg2O, it's always Mg2O. It's never Mg2O3 or anything like that. Okay, and then we remember if there is no subscript, the number of atoms per molecule is assumed to be 1. So where do these numbers of atoms in the chemical formulas come from? How do we figure this out? How do we get the correct ratio of one element to another? Okay, and so the easiest type of compound to set up rules for is going to be ionic compounds. And in fact, we're not going to talk about where we get the formulas for the covalent compounds from. That's a little more difficult. So we'll just talk mostly about ionic compounds related to their formulas. And we remember that these are compounds in which there is transfer of 1 or more electrons in order to create the bond. Okay, the formation of the bond comes about because we have transferred electrons from a metal to a nonmetal, and that forms the ions, and then the ions get together and form the bond. Okay, now before we determine the rules for these, there are several things you should always remember about ionic compounds. We usually describe ionic compounds as consisting of 2 components. I have a positive component and a negative component, and I'm going to call the positive component the cation. Okay, it's not cation or cation, it's cation. And I can remember this with a simple mnemonic. If I think about cat paws, the paws of a cat, a PAWS, right? Those kinds of paws. I can say cat paws is like cat ion is a positive ion. Okay, so I can use the words cat paws to help me think of cation as being positive. Okay, a negative component is going to be called the anion. So I've got 2 components. I've got a positive component and a negative component. And when I was growing up in high school, that was when the first Star Wars movie came out, and Anakin Skywalker in that movie was a negative thing. So anion, Anakin Skywalker, negative. Okay, that's how I remember positive and negative as far as cation and anion go. Okay, now we also remember that the cation becomes positive because it gives up or loses 1 or more electrons, and the anion becomes negative because it takes 1 or more electrons. And then the cation can be one of 2 things. Almost always it will just be an element, right? It's just going to be a metal element that's lost 1 or more electrons. This will always be a metal. But it could also be a polyatomic ion, and we said there was only a single polyatomic ion. That was the ammonium ion, the NH4 ion. Okay, now it's not letting me put in a subscript here, so the subscript NH4 is what that's supposed to be there, NH with a subscript of 4. Okay, so cations can either be, and usually will be, metal ions or a polyatomic ion, the only one of which is NH4. The anion can also consist of elements that have gained 1 or more electrons. This will always be a nonmetal, or it can be a polyatomic ion, and we've seen lots of those. Okay, we've listed out a fair number of those. So we've got a positive and a negative component, and our goal in all of this is going to be to create formulas that create the same number of negative charges as we have positive charges. Okay, we need to match the number of positive charges and negative charges in the formula. So the charges are said to balance out, and the overall compound is neutral. So again, we have 2 components. We have a positive and a negative component, a cation, an anion component, and the positive will always be on the left, the negative will always be on the right, and the cation will always be a metal, and the anion will always be a nonmetal. And the way to remember this is that cations, metals and transition metals are always on the left side of the table. Okay, so cations are metals and metals are on the left side of the table. Anions are nonmetals and nonmetals are on the right side of the table. So I need to fix that. Hold on a sec. Okay, so now this says cations are metals and metals are on the left side of the table. Anions are nonmetals and nonmetals are on the right side of the table. So we've got all kinds of visual clues from the periodic table that helps us burn these things into our brain here. Okay, so cation, anion, positive, negative, left, right, metal, nonmetal. These are all things that are going to help us visually and sort of mentally burn these things into our brain. So the strategy to determine the subscript for each component of the compound is this. I've got a strategy. How do I figure out what the formula, the chemical formula, is going to be? So the first thing I have to do for ionic compounds is determine the charge on each ion, and we'll go through a bunch of these here in a little bit. If it's a metal, it will always be positive. And remember, if it's in column 1A, it'll have a 1 plus charge, 2A, 2 plus charge, 3A, 3 plus charge, and so on. Okay. If it's a transition element, we'll have to look it up on the transition metal table. And again, we'll go back and forth through this to see how we're going to do this. If it's a nonmetal, it will always be negative, right? And in 4A, it will gain 4 electrons, so it'll have a 4 negative charge. In 5A, I have 5 spots that I've already taken up. There's only 3 left, so I'll take 3 electrons and have a 3 negative charge. In 6A, I will gain 2 electrons because there's 2 spots left in the outer shell, and I'll have 2 negative charge. And then in 7A, we'll have a 1 negative charge. If it's a polyatomic ion, for now, look it up in your polyatomic ion table, although honor students be memorizing these. NH4 will be the only positive one. All others will have a negative charge. So for all of these, I'm going to first write out the charges. Then we're going to determine the number of cation and anion particles necessary at each of their charges to make the total number of positives and negatives equal. Okay, I have to have the same number of positive charges for my cations as I do for my anions. And we've got several ways to do this, and we'll illustrate these. If the negative number of charges for the anion already equals the number of positive charges for the cation, the formula is already balanced and you just need one of each. Neither ion needs a subscript. If the charges are not equal in value, you can multiply the numbers of the two charges together. This will give you the total number of positive and negative charges needed to balance the formula. Then determine how many of each particle is necessary to give you that many charges, and that will be the subscript for the ion. Again, we'll go through this a lot. And then a quick way to accomplish the same thing as number 2 is simply to just switch the numbers of the charges and use the switched numbers as subscripts. And if you do that, if one of the numbers is 1, that ion doesn't need a subscript. If both numbers are even, reduce the numbers to the lowest amount possible. Okay, so we've got some practice here. And dang, it looks like I'm already about out of time here. So I'll stop this video now, and then the last video we'll just go through lots of these, okay? So let's stop the video and go through these.